So that has started. So I guess we can start a meeting. It's my great pleasure to host today another meetup with Marek Ray. Marek is a machine learning lecturer at the Imperial College of London. He's also a visiting researcher in Cambridge and co-founder and chief scientist officer. I got it right, yeah. In transformative AI startup. Marek is working on natural language processing problems for quite a while. Has a great experience both in industry and academia. And today he will talk about something that I guess everyone is thinking when we are training all of our transformer models, which is like how much it's actually learning versus how much the model is just memorizing some stuff in the data. And I guess it will be super interesting for us from the Polish geographical, I guess, background, because like we most of the time we're working in way low resource data set level than in English. So yeah, floor is yours, Marek, and super happy that you joined us.
Great, thanks for inviting me, and I'm very happy to present here. Yeah, just to note, my first name is Polish, but I'm not actually Polish myself, so I will be giving the presentation in English. I'm actually from Estonia originally, so unfortunately I don't speak any Polish. So this work that that I'll be talking about today is on memorization and generalization in pre-trained language models. And it's work that was done mainly by Michael Tanzer, who was a master's student at the time and is now a PhD student. And it was supervised by myself together with Sebastian Ruder, who was working at the time at DeepMind. So yeah, Pavel gave me a nice introduction already, but I'll walk through a couple of points as well, just to share a bit of my background and give you an idea of where I'm coming from. I'm a lecturer of machine learning at Imperial College London, and I work on topics such as transfer learning and representation learning for natural language processing. I am also a visiting researcher at the University of Cambridge, and I'm a scientific advisor for Transformative AI, which is a medical technology startup. Before that, I was a senior research associate at Cambridge. For a few years, I also worked as a researcher at SwiftKey, which is now Microsoft, well, part of Microsoft. There I worked on neural network models for text prediction and correction on the phone. So these predictive keyboards and creating a neural model for that. And that's where my interest in kind of pre-trained language models originally came from. And I also did a PhD on unsupervised and semi-supervised learning methods. So the talk today is going to be about presenting different experiments that we did with pre-trained language models and seeing how they behave under different settings. And broadly, we can separate the experiments into two categories. One is trying to see how they are learning to generalize when dealing with increasing amounts of noise in the training data. So how can they ignore the noise while learning the patterns? And the second part is how are they learning to memorize when dealing with very few examples of a particular label. So sometimes we don't want the model to just ignore individual examples. We want it to remember these examples, and then how are the pre-trained language models performing in such settings. So the general goal is to understand better the learning process of these widely used models. There's already quite a lot of work on investigating what these models are learning. So for example, through probing, we can see, are they capturing things like named entity information or dependency parse information or something like that. But there's very little work on looking at how they're learning. So how how are they capturing different information, and how is this changing throughout the training?
The question is related with recording, so I'm just responding right now.
Okay, yeah, I was just
I'll handle
about
that, yeah.
I was just about to mention that I can't see the chat and I can't see you. So if there are any questions, feel free to ask them with voice. Otherwise, I won't be able to see them until the end of the talk. But yeah, investigating how these models are learning in different settings. You probably are already familiar with pre-trained language models. They're just such a common part of NLP these days, but because they are also a very central aspect of this work, I have a couple of slides here to kind of give an underlying motivation for them as well. So the idea is that we can learn general language patterns from huge amounts of data. And we can do that using unsupervised objectives or unsupervised pre-training, and learn really high quality word representations and feature detectors into our neural language models. And then we can transfer these over to a new task or a particular task that we're interested in. And we can either keep these language models in the new task fixed, so we can freeze them and put some new layers on top, or we can connect them together and just kind of optimize them end to end throughout. These are a really great resource. They allow researchers to build on other researchers' work. There are some models that would take hundreds of thousands of dollars to train, but someone has done it once and made it available online, and then everyone else can just download it and integrate it into their model and continue from that point, essentially, to build upon the work that has already been done. And for example, in the Hugging Face repository, there's already over 20,000 different pre-trained models available, and each of them has a slightly different architecture. They're trained on a slightly different data set or using a different objective. So each of them has a slightly different properties, how they behave, what they're good for, where are their weaknesses. There's probably a good model out there if you're thinking of a task and starting point. The kind of a prototypical pre-trained language model is now BERT, basically. So BERT stands for bidirectional encoder representations from transformers. It was proposed in 2019, it wasn't really the very first such model, but it was the first that pre-trained the model on really huge amounts of data and then made it really easily available to other researchers. So BERT really made this area to take off, basically, and easily accessible to everyone. And the idea is broadly that we feed some sentences into the model. So in this case, we're giving it two sentences, sentence A and sentence B. We separate it into word tokens, or actually in practice, sub-word tokens. They get mapped to vector representations, then fed into multiple transformer layers, which contain self-attention. So these layers contain a lot of parameters and a lot of operations, which are all optimized during training. And then at the top, we optimize this model with unsupervised objectives, namely two different objectives. One is masked language modeling, where we're masking some tokens in the input and asking the model to predict these missing tokens during training. And next sentence prediction, which is basically a binary classification task of deciding whether the two sentences that were given as input actually occurred in that order in the original data. And both of these are really good objectives because They don't require any additional annotation. We can just take random text from the internet, from various sources, and we can use that for training this model. And once we've trained the model, we can take it and then fine-tune it for all sorts of other tasks. So we can train it for NLI, named entity recognition, question answering. So we start with the original model, we change the objective at the top, we give it new data, and we fine-tune all the parameters in the model, and now it becomes a new model for a new task. There are many models that are similar to BERT or are like modifications of BERT. So there are models that are trained on even more data. There are models that are more compact and resource efficient. But they all largely behave in a similar way. In this work, we mainly focus on BERT as it is kind of a prototypical pre-trained language model, and it probably is still the most widely used one out of all of them. But we do some experiments also on Roberta and DBERTA to verify that the findings that we do have actually hold for other types of pre-trained language models as well. Now, when pre-trained language model is fine-tuned, then it really needs to strike a careful balance between generalization and memorization. So in order to generalize to unseen datasets, we definitely wanted to capture like real underlying patterns in the data, and not just pick up on individual examples and memorize them. But on the flip side, in many cases, we don't want the model to just throw away rare examples either, because natural language has this really long tail of infrequent cases. And if we don't cover any of them, then we're going to be losing out on a lot of information. And just because something is rare doesn't mean that it's incorrect or it's definitely something that the model should be discarding. So essentially, we still want the model to be able to learn from individual examples. And we'll investigate this balance in the current pre-trained language models and how this balance shifts during the process of fine-tuning. The data sets that we use in this work are all on the task of named entity recognition. Named entity recognition is a task where for each word in the input, we want to assign a label indicating the type of that word. So in the sentence, example sentence here, we want to assign Jim a person tag, Acme Corporation an organization tag, and 2006 a time tag. And then everything else is just this default label of not an entity. This task is used for many different information extraction applications, for example. Why we use named entity recognition in here? Reason one is that it is widely used to benchmark pre-trained language models on the tasks of sequence labeling and structured prediction. So it's a very common task to do, but also it has a good property that the labels are naturally imbalanced, and this actually allows us to better construct some of the experiments that we're going to be doing. It's easier to kind of shift the balance and control the balance even more if we want to evaluate only on some rare labels, and it's easier also to introduce some noise into the dataset when needed. And the datasets that we use are three. The Connell 2003 dataset, which contains news data. The JNLPBA dataset containing biomedical abstracts, and the WNUT dataset, which contains Twitter data. And the WNUT dataset is particularly difficult for models, pre-trained language models, because it contains a lot of information that's basically not present in the training data, but the model still needs to figure it out in the test data. So it can't just kind of rely on everything that it has learned in the training data. It needs to generalize to unseen examples, basically. So the first experiment is over here, and what we did here is train a model on the Connell 2003 dataset and test it on the validation set. But during training, we add some label noise. So we basically randomly select some tokens. We change their correct label. So it's kind of mimicking a situation where we're dealing with incorrect annotation. But then we test still on clean data, and we see how well the model manages to learn from this noisy data. And so the red lines represent training performance. The blue lines represent validation performance, and the darker colors in each of them represent higher levels of noise. So the first observation that we can do is that the training process naturally separates into 3 different stages here. So there's a stage 1 where the model is just actively learning. The performance on the training data goes up, the performance on the validation data goes up. And you can see that the more noise there is in the training data, the worse it does on the training data, basically. So that makes sense. Then there's a second stage where basically we observe that everything kind of stops, as in the model isn't, it's internally probably still learning, but it's not really making any new predictions that it wasn't before. So you can see that in the second stage, the training performance is very stable, and the validation performance is also very stable. And then in the third stage, the model activity starts overfitting, and the training performance starts going up again, whereas the test performance, the validation performance, starts actively dropping, corresponding to overfitting. So this is kind of what we expect, in the sense that we expect a model to learn until it reaches a point where it starts overfitting, and then validation performance would start going down, and training performance would start going up. But what this kind of second stage is somewhat unexpected, because normally this just happens gradually, as opposed to a very separate barrier between the 2 stages. So a second finding that we did, that we noticed, is that the model is particularly robust to noise. So you can notice that the training performance can be very low, with something like 40 or 50% of noise, but the validation performance is actually still very high. And even with very high levels of noise, it gets very similar performance. So with 50% noise, the darkest blue validation line drops a bit, maybe a bit under 10%. But everything else, all the other blue lines in the second phase, are actually very close to each other. So it almost doesn't matter how much noise is in the training data, as long as the test data or the development data is clean. The model actually learns very similar patterns from the training data, and performs reasonably well. So yeah, adding 30% noise to the Connell 2003 training dataset caused only a 0.9% decrease of validation performance. But that only applies in the second phase. So as you can see, in the third phase, the validation performance does drop at different speeds. So the more noise we have, the faster the performance drops. We were also interested to see how the model behaves.
May I have a question?
Sorry?
May I have a question about the previous slide?
Yeah, sure.
All models are exactly the same, so only the difference is how many times the model is trained?
Yes, the model architecture is the same. It's the training data that is changed. So
we have overfitting when we train model too much.
We claim what?
Too long. When we train model too long, we have overfitting.
Yeah, exactly. Yeah.
Why? Do you know why?
Oh, so because so as you can see, the lightest blue line doesn't actually overfit. So it so this is trained on the clean data. But
Okay.
if we have data that contains noise, then the model gradually starts memorizing the noise, as we'll see in the next slide, at the cost of development performance.
Okay, but why this is depend from the time of training? Why we don't the model don't recognize this noise on the beginning?
I mean,
on the phase 3.
So I mean, so that's a good question. That's a property of the model. So that's what we're trying to kind of demonstrate that the model does with these experiments. That it in phase 1 it manages to learn the common patterns, whereas in phase 3 it's learning everything that doesn't match the common patterns. So the explanation for that would be that anything that's kind of very frequent gets optimized and distributed between the millions of parameters of BERT. So it gets much more training signal during the first phase, and it takes a lot longer to influence the model into some unpredictable direction, basically. And these are the examples that are learned in the third phase.
Okay, but the noise is created or when you train and use the same data in each epoch, or you add a different noise in each epoch?
It's the same noise in each epoch.
Okay, thanks.
So yeah, so this is a graph that shows the performance, the other side of this performance. So this is looking at only performance on the noisy data points. So these are essentially the data points that have incorrect labels. And you can see that in phases 1 and 2, the model basically manages to ignore these data points completely. So it starts off at the level of a random classifier, and then immediately the performance goes to 0 on these noisy data points, as it should. And it manages to hold that for quite a while, and then only at the third stage it starts learning them. And this kind of step function indicates that it doesn't really find a pattern for them. It instead memorizes a certain number of noisy data points at each epoch. So that's where this step function comes from.
There's one comment from Tomasz. It's a bit surprising to me that the scenario with the highest noise rate seems to be the most prone to overfitting. I don't know if you want to comment on that.
I mean, I would say that's completely expected, actually. So the highest noise means that there are the largest number of noisy data points in the training data, which also means that, like, because the size of the training data is the same, so that means there's also the smallest amount of clean data in that training data, right?
I guess what you were hinting, Tomasz, at is that, for example, with the dropout, right, we are expecting better generalization with the more noise in the dropout, right? But I guess that the quality of the noise is different here versus what we do with the let's say dropout.
Maybe I can clarify. Yeah, I think like mostly from, for instance, computer vision, when we use some technique of augmentation, we add some noise to counter overfitting. So maybe like the question is, what's the nature of this noise? Because if we kind of have different type of data we need to fit, then it would be expected. But I think if we use some kind of noise, I don't know, it could even help with some tasks for overfitting.
Yeah, absolutely. I think I know what you mean. So this is this does certainly mean that the type of noise is important, because normally if we're doing regularization, then we would be adding some noise to the input, and it would be quite a subtle noise. Whereas here we're actually introducing labeled noise. So the input remains the same, but the label changes. So that actually means that the model receives an incorrect training signal. So that's definitely gonna hurt the model as opposed to help it, I would say.
Okay, thank you. It clarifies a lot.
So yeah, this graph also demonstrates how in phases 1 and 2, the model manages to pretty much ignore these noisy data points, but then in phase 3 it starts to memorize them actively. We wanted to see what happens in the model if we don't do pre-training. So this is same graph, but for a model without pre-training, same architecture, but the BERT model is trained from scratch, as opposed to being pre-trained as a language model. And you can see that the same findings don't really hold anymore. So there's no kind of clear second phase, because the training performance keeps going up throughout the process. And the robustness of the model isn't the same anymore either. So when there's more noise in the data, the darker blue lines on the performance on the development set is going to be lower as well throughout the training process. So we don't have this nice property anymore that if we stop at the right point, then the model performance will be optimal pretty much regardless of noise.
Sorry for interrupting, Marek, but another question, Mateusz. Have you tried to train BERT models for over 50 epochs? In one task, I encountered a very unstable result during the first epochs, but after many more, it seems to stabilize.
Oh, that's an interesting question. No, I haven't really heard people doing that. So lately, what people seem to be doing is just training BERT models for like 2 epochs, and it has kind of become standard, and I'm not even sure where it came from. And it's like this, well, the earlier graph would indicate that 2 epochs is actually a good amount of training to do. I haven't tried training it for like 50 epochs or something. We did go further than 10, but probably not 50.
Yeah, so the question is based in the initial between 3 and 5, 6 epochs, the F1 score was varying by about 0.5, 0.3% every time I ran the same fine-tuning task. But after I actually went to Stack Overflow, and somebody suggested running it for many more epochs, and it actually seemed to be working. So I wanted to hear a perspective on this one.
Okay, but did it stabilize at the highest rate, or did it?
Well, it was about it was one of the better results, but it was very stable. So I was running the same fine-tuning task for 40 epochs for a couple of nights, and it was giving me very consistent results.
Okay, yeah, that's very interesting. Could be an interesting follow-up work to investigate even the later tail of BERT training. Yeah. So yeah, in this graph, we found that much of this property of BERT is due to pre-training. Yeah, basically it shows that the same doesn't apply to the same model architecture without the pre-training in the model. So this is the graph of showing performance on the noisy data points without pre-training. And again, you can see that like the performance does initially drop, but it doesn't quite go to zero at all, and it starts going up much sooner than it did before if we're not using a pre-trained language model. We also wanted to test other types of models. Here is a graph for Roberta doing the same thing. You can see that the training performance does stabilize really well, and actually the validation performance is even more stable than with BERT. So there's starts to be a bit of a drop in the third phase, but not quite as dramatic as with BERT. So Roberta manages to hold the robustness even better than BERT. And with dBERTA, the results are very similar to BERT. So there's a very clear stabilization in the second stage of training, and then training performance goes up in the third stage, while validation performance goes down. And in the second stage, there's also very good robustness. So performance on the validation set is not largely affected by the noise in the training set, so as long as we stop the training early enough. We did some experiments on other data sets as well. You can see more of them in the paper and also in the appendix of the paper. So here we did an experiment with BERT on JNLPBA, and the results are largely similar. So the training performance stabilizes in the second phase, but most notably, the development performance is very similar on all the variants, regardless of the noise in the training data. So as long as we stop training soon enough, we don't really need to worry about label noise. So given that BERT manages to do this like really nice separation into different stages of training. So it has a clear stage where it's learning general patterns, and the clear stage where it's learning like noisy examples and outliers. We want to see if we can actually use that to automatically detect the noisy data points. So what we do is we train a model on the noisy data for 4 epochs. So it's going to lie inside the second stage of training. And then we collect the losses from all the data points, and we assume that the losses form 2 clusters, that the noisy ones are going to have higher values and the clean ones are going to have lower values. And then we just optimize a threshold to separate 2 clusters in these values. We're optimizing for a threshold T that separates, that has the shortest square distance between the threshold and the mean of the upper cluster and the mean of the lower cluster. And visually, you can see that here. The blue, so this is a histogram of the loss values, and the blue ones are the clean examples, and the red ones are the noisy ones. And there is a little bit of mixing happening. There's a bit of red on the left side and a bit of blue on the right side, but largely there's a very clean separation between the loss values. And the dotted line here is then the optimal threshold for the two. And when we formulate this as a classification problem, we can get really high F-score. So over 90% and even over 95%, depending on the level of noise. And we don't really need to know the level of noise in advance. It just separates the losses into two clusters, basically. So yeah, essentially we found that because BERT learns clean and noisy data points at different stages of training, we can actually use that and analyze the loss levels in order to separate noisy examples from the clean examples. Now, we also experimented and investigated with forgetting of learned information. So when we're evaluating model performance in the final stage after it has been fully trained, then that doesn't necessarily give us the full picture because the model can internally learn and forget data points multiple times during the training process. So we're interested to see what's happening there during the learning. And we define two counts, so like two data point types. So one is a forgettable data point, and that's a data point that's classified correctly, at least in one epoch, but then later forgotten or misclassified in a later epoch. So it may or may not be relearned later. For this count, it doesn't matter, but we're interested to see like how many data points does the model learn initially, but then forget later, like rewriting with some other information. And then a learned data point is a data point that is classified correctly in at least one epoch during training. In previous work, researchers have investigated this kind of forgetting of data points during training, but in the context of image models. And they found that in the image modality, it actually doesn't matter much which kind of architecture you use, as long as you're using the same data set. So you can train different architectures on a given data set, and you would have roughly the same number of forgettable data points. So it's more the data that determines how forgettable a data point is. Whereas we found that that conclusion didn't really hold in when working with pre-trained language models and BERT in particular. So we're comparing three different models here: a bi-LSTM model, then a non-pre-trained BERT, and a pre-trained BERT. And if you look at the column of forgettable data points, then you can see that an LSTM forgets a whole lot more data points than a BERT model does. So that means during the LSTM model optimization, it can learn a data point, but then it gets overwritten by some other data point later in the training. It forgets this information, then relearns it, forgets it. Whereas with BERT, it's quite a bit more stable. So it learns the data points that it wants to learn, that it remembers later in the training as well. And when comparing the non-pre-trained BERT with the pre-trained BERT, there's again a visible difference. So pre-trained BERT helps it forget even less. So it kind of focuses BERT to only learn the information that it wants to learn from the data. Now, learning these patterns, learning general patterns for a task, usually means learning the most frequent patterns that separate the class. And we've seen that pre-trained models are really good at this. BERT can perform really well at learning the general patterns and then leaving the memorization of noisy data points somewhere later in the training, by which time we've probably stopped training altogether. But what happens if there are only a few examples of a particular class? So we don't really want the model to only learn based on frequency. That would mean that any low frequency examples just get thrown away. So we investigate this and we evaluate model performance on datasets where a label occurs only a small number of times. And we do this by explicitly constructing the training set in a way that a certain label just occurs a few number of times. So we can exclude sentences from the training set containing a particular label down to a given number that we want to keep, basically. And you can see BERT performance here. So this is on Connell 2003. And on the x-axis, you can see the number of training sentences containing a particular label. So we're looking at labels miscellaneous and location in that dataset. And then on the y-axis is the model performance on predicting that particular label in the validation set. And you can see that when there are a small number of labels available, then BERT doesn't really predict that label at all. So in this case, it's if there are 25 examples or fewer, then BERT doesn't predict that particular label any time in the validation set. If we go higher than that, then the performance starts to increase. And once we get to about 100 examples, then performance starts to stabilize at a reasonable level. So that means we're kind of missing out on some low frequency examples and low frequency information in our data sets. Similar results on the JNLPBA dataset. So here again, you want to be looking at the solid lines at the bottom, and these indicate the performance trained on the few-shot training data. And here, up to a level of about 50 training examples, the model doesn't predict that label at all on the validation set. Once we go higher than that, then the performance starts to go up fairly linearly. So this seems a bit of a weakness, that the model is kind of saying if something doesn't occur at least 50 times in the data, then it's noise and we want to forget about it altogether. Humans are able to learn from something like 1 or 2 examples. So we would like to give our models the ability to do something like that as well. So we tried to do a modification of BERT to see if that would help improve performance. So what we did was the method basically calculates a prototypical representation for each possible label based on the training data. And then given a new data point, predicts the label based on how close it is to each label representation. And we can do all of this on top of BERT, so the representations can all be learned. So it's trained end-to-end. And this is based on prototypical networks and adapting them to work with BERT and with sequence labeling. So in practice, the way it works is we take our training data, we split it into 2 parts, support set, which we use for calculating the label representation, and a query set, which will act as the unseen data points during training in order to optimize our model. And then we, based on the support set, we calculate centroids for each possible label. So each label has a vector representation. We then compute the distance for each example in the query set, and between that example and the centroid of every label. So we know how far a particular data point is from the centroid of a label. And we use Euclidean distance as the distance metric here. And now we have a score for each label. We normalize that using softmax. And this gives us a probability distribution over all of the labels. And the network is optimized with cross entropy, and it can be back propagated end to end. So the whole thing is optimized. And it's still using BERT for representations. It doesn't actually introduce any additional parameters to the model. It just changes the way that the representations are used internally. During training, we sample the support set and the query set randomly from the training set at each iteration. But during testing, we use the whole training set as the support set, and the test examples go all into the query set. So we make predictions for the query set based on the support set. For named entity recognition, we don't really want to learn a single representation for the default non-named entity class, because it doesn't really make sense. There's nothing really common about the non-named entity words. They represent all the words that don't belong to a particular entity. So we would expect them to be distributed across the whole representation space. And instead, we represent that class as one single trainable parameter in the score distribution, while all the other class predictions are represented by the distance from the centroid. And you can see the results here. So this is evaluating BERT versus this proto-BERT modification in a few shot setting. And the lines at the bottom are, again, regular BERT in this setting where there are only a few number of training examples for a particular label available. And the solid lines at the top are the modification using this proto-BERT approach. And you can see that when there are very few examples available, this method definitely improves performance on these labels. So it prevents the model from kind of being overwhelmed by all the other labels, and it still has a distinct representation for this low frequency label that allows the model to make predictions for that label. And with something like 25 training examples, the performance difference is actually over 50% F1 score. And as we get more training examples, this performance difference decreases and becomes roughly comparable, which we would expect because we don't really expect this to help in a high frequency case, but it's more towards helping the low frequency labels. In the interest of time, I'll skip this slide and I'll go straight to this one. So here we actually evaluated BERT against the proto-BERT modification on the regular named entity recognition benchmarks. So here, there's no special kind of filtering or modification for low frequency. We just wanted to see how well it would do on the regular data set. It doesn't necessarily have any low frequency labels. And you can see that the method helps a bit on Connell 2003. It doesn't work as well on JNLPBA, probably because, as I said, there aren't any as many low frequency labels in that data set naturally. So the regular model actually performs better. but it gives a very large improvement on the W0 dataset, which is notoriously difficult for models that are just learning frequent patterns from the training set. And it actually gets quite close to the state-of-the-art result on that dataset. So to conclude, in these experiments, we investigated generalization and memorization of pre-trained language models in situations with noisy labels and few-shot training examples. We found that bird training gets separated into several different distinct stages, with learning of general patterns in the first stage. Then there's a second stage of stabilization and a third stage of learning noisy data points or outliers, where data points are literally memorized into the model. And this makes BERT very robust to label noise. So if we stop at the right point, we can get optimal performance even with very high noise levels. And we found that we can even identify the noisy data points simply based on their loss during the training. However, this great generalization property comes at the cost of low performance when it actually needs to remember specific information about data points. And when we're dealing with low frequency or few shot settings, then regular BERT isn't performing particularly well, and we can use some modifications that make use of the BERT representations in a different way in order to improve performance in these few shot settings. So that's it from me. If you're interested in learning more about this work, the paper is up on arXiv, so I encourage you to take a look. Yeah, thanks very much, and very open to any questions.
Feel free to speak up at any time. In the meantime, I'm gonna take advantage and maybe not a question, but rather a comment, is that this is a fantastic, I guess, tool to the noisy data, where you basically fine tune for, let's say, 2-3 epochs, and then you target all of these potential things that could probably be labeled noisy. And that's like super helpful for production data sets that we usually have. So yeah, it's a really cool idea.
Yeah, it would be interesting to kind of try this on real data. Of course, these experiments were done with like kind of synthetic noise, just so that we can control the level very carefully. But yeah, it would be interesting to do this with real data, where we actually kind of rank the data points based on their loss after a few epochs, and then have them manually annotated and see if they're actually noise or not.
The other thing what could be done is to hallucinate that data with, like, I don't know, GPT, and then see if it's, BERT is also the loss can also quickly be divided for these two. Mateusz, yeah, go ahead.
Yeah, I'm in the process of creating a named entity dataset, and you mentioned in your presentation that BERT may never be able to predict a particular label if there are too few examples. So I would like to ask you to quantify what too few means. Do you have an estimate for this?
Well, I mean, it's gonna depend on the data set. So we saw from the slides and the graphs that, I mean, on the Connell 2003 data set, it ended up being 25 examples, and on the JNLPBA dataset, it was 50 examples, for example.
Okay.
So, but I mean, higher counts are needed in order to have like reasonable performance on that label, of course.
Yeah, definitely. And so I would like to build up on this question. So is there a few shot model for NLP that perhaps is able to memorize a named entity with fewer examples than 50 or 40, or there is no such model?
I mean, well, for example, the model that we proposed that was kind of doing that, so it was getting reasonable performance on these rare labels. I'm sure there are other models as well that have been proposed for few-shot learning. We didn't really do a full comparison of those, as the focus of the paper was more about learning what BERT does as opposed to kind of engineering the best few-shot case. But it was just an additional experiment that we did too.
Okay, thank you very much.
Yeah.
Hi again. Thanks for interesting talk. So I have a few more questions about the first part, about this introducing noise. So were there any pattern in this noise, or it was just changing the random label, like random share of labels?
Just random, yeah.
Okay.
So it was, yeah, synthetic noise, randomly sampling a new label.
Yeah, because I think it was shown that because you went up to 50%, right? So it's maybe could be interesting to see what happens after 50%, whether we can learn this noise or not. Because I think that there is some experiments which had some patterns in the noise, but then when with like introducing enough noise, we could really probe for the noise, not for the information we wanted. And I think this was one of like the main points of criticism of like probing, of looking what BERT is learning, because the information we want to find, we can find it because we have enough parameters to find it. So,
yeah, absolutely. Yeah, I think if the noise had some patterns in it, then it would become a somewhat a different task, because it would be more difficult for the model to distinguish like what's a correct pattern and what's an incorrect pattern, right?
And it was also quite interesting that Roberta behaved quite differently. So we didn't see this overfitting. Because you use BERT large, right? So
that's a good question. I don't recall off the top of my head, because it was the student who actually implemented the experiments,
sure.
and but it's I'm sure it's written in the paper.
Yeah, sure. So it's like shouldn't be even like the number parameters which changes. So it's like interesting what happens there, but the results were so different.
Yeah, I mean, to some extent they were similar in that there was a similar kind of stabilization and robustness, but the drop off, I guess, was much slower. So it could be that it actually happens much later in the training. So it maybe training to 50 epochs is a good idea, and something weird is going to happen there for Roberta.
Yeah, thank you.
Any other questions?
So maybe if there's nothing else, then I can ask one more.
Go for it.
You showed that there's on one slide that you can distinguish between the noise examples and the clean examples based on the magnitude of the loss, right?
Yeah.
So this could work, but only if we don't mix like noise and clean examples in one batch. So it would be problematic, or we could still somehow find out which examples in one batch are noise or clean, because like
so we calculated the noise per data point. So even though you're kind of like back propagating for the whole batch, you can still measure loss at individual data point as well. So I'm pretty sure it was the data points, both noisy and clean, were mixed together in each batch, but just yeah, we can kind of extract the loss for each data point separately.
Sure, thanks. That's great.
Awesome. I guess we are slightly past 6, so we can call it a day. Fantastic talk, Marek. I will send you the recordings first for approval, and then we're going to share it on YouTube if anyone will be interested in checking the details again of some parts of the presentation. Have a lovely afternoon, and see you guys next month, hopefully.
Okay. Thanks very much, and yeah, good seeing you.
See ya.
Thank you.
Thank you very much. Bye.
Thank you. Bye.